Hi everybody, this is our lecture on section 6.3, the fundamental theorem of calculus for line integrals. So recall the ordinary fundamental theorem of calculus. Should be capitalized. Fundamental theorem of calculus, which is the integral from a to b of f prime of x dx is equal to f of b minus f of a. Right? You just find an antiderivative, any antiderivative of the function, and you take the difference at the two endpoints of the integral. So now consider a gradient vector field. In 2D or 3D. Okay. Gradient fxy, which is the partial derivative of f with respect to x, partial derivative of f with respect to y, or the gradient of a three-dimensional, three-variable function for a three-dimensional vector field, partial f, partial x, partial f, partial y, partial z, or partial f, partial z. And a continuous curve, not broken, C, given by, well, either r of t in two dimensions, right, which is given by x of t, y of t, or in three dimensions equal to x, t, y, t, z, t for a less than or equal to b, or a less than or equal to t, less than or equal to b. All right, by definition, the line integral over c of the gradient vector field dot ds, or dr, if you will, say dr this time around, is equal to the integral from a to b, okay, the gradient vector field, right, which is, we'll do it in three dimensions. Well, let's write it this way. Gradient vector field at r of t, whatever that might be, dot r prime of t dt. Right? So this is equal to the integral from a to b. Well, we're just going to write it like this. Partial f, partial x, partial f, partial y, partial f, partial z. Of course, x is a function with respect to t, as is y, as is z, but it doesn't change what the gradient is. Okay, the gradient is simply this function, or this vector field here. Dot r prime of t, which is the derivative of these, dx dt, dy dt, dz, dt. Look familiar? Right, that's a dot product. So let's evaluate the dot product. It's integral from a to b, partial f, partial x, dx dt. This product plus this product plus this product, right? Plus partial f partial y dy dt should look even more familiar now. Partial f partial z dz dt dt. Right? Well, what is that? Right? By the chain rule, what is that? Recall the chain rule. Put it over here in red. Maybe move it over a little bit. All right. So the chain rule, right? What do we have here? We've got f is a function of x, y, z, and then x, y, z are all functions of t, right? Because we're looking at f of x, y, z, the gradient vector field, f, just on r of t. Just on r of t, right? It's the vector field just on r. So it's all a function of t. So f is a function of t, so df dt is just equal to this expression here. Partial f partial x dx dt plus partial f partial y dy dt plus partial f partial z dz dt. And that's exactly what we have here. So this is the integral from a to b, right? The derivative with respect to t of that original function f x y z dt. Right? So by the ordinary fundamental theorem of calculus, so it all just boils down to the ordinary fundamental theorem of calculus. This is equal to f at the beginning endpoint, where x, y, z is simply equal to r of b, minus f at the ending endpoint, which is r of a. How about that? Right? So, couple different interesting consequences of this. So this is the fundamental theorem of calculus. For line integrals, let's rewrite it. So in summary, right, given gradient vector field f, x, y, z, and continuous curve C from, well, we'll not even mention R, A, B, C to X, Y, Z, like that. The integral along C of gradient F dot dr is just equal to F of, so let me draw a picture here. So here is C, and this is the point A, B, C, and here's the point X, Y, Z. Right, so C is just any continuous curve from here to there. It could be that one, you know, or it just could be the straight line. Doesn't matter which it is. That this is just equal to f of x, y, z, the end point, minus the beginning point. Right, so the integral, or the derivative, is just like the ordinary fundamental theorem of calculus. the integral of the derivative of the function f, so gradient is kind of like a derivative. The integral of the derivative is the function at the end minus the function at the beginning, just the difference of the endpoints. Right, and it doesn't matter what the curve is, a straight line or some loop-de-loop or something that goes like this. I mean, whatever it might be. It doesn't matter. It's always the same. So, for example, by the way, this is for the vector line integral. There is nothing that simplifies the scalar line integral. Okay, again, as I was saying, the vector line integral is more well-behaved. And this is exactly what I mean by that, is that there's, theorems that kind of simplify it in various circumstances. The scalar line integral, nothing. It just is what it is. Okay? It just is how it's defined. So, for example, here we are. So, let's calculate the integral along C of 2xy, comma, x squared plus y dot dr, where C is any continuous curve from 0 to doesn't have to be smooth. When I'm drawing is smooth, but doesn't have to be. Matter of fact, let's unsmooth it a little bit. Oops. Yeesh. Let's make it a little unsmooth. Right. Zero two to the point 3 minus 1. Okay, so calculate this. Do the calculation twice. All right, once by the fundamental theorem. And once by a choice of C, or C. So we're going to calculate it in two ways and see that we get the same thing. Okay, well, first of all, this is a gradient field. Here, P is equal to 2xy. Q is equal to x squared plus y. Right, so now check P of y, that's equal to 2x, and Q of x is equal to 2x. So this vector field is conservative. Right? It should be the vector field, the gradient vector field for some potential function. Okay, so P, right, because the derivative of P with respect to y is 2x, and the derivative of Q with respect to x is 2x, and those are the same. So P, which is supposed to be for a given potential function, the derivative with respect to x, to xy, if we take the antiderivative of this, it gives us that fxy is equal to, well, antiderivative with regard to x, is x squared y plus an arbitrary constant. Right? What's the arbitrary constant when you're taking the derivative with respect to x? It's not just a constant, but it's any function just using y. It's any expression using y. Right? That's going to be a constant. And f with respect to y, partial derivative of f with respect to y, is supposed to be equal to q, which is x squared plus y. So this tells us that fxy is equal to antiderivative with respect to y, x squared y plus 1/2 y squared plus an arbitrary constant, which is an expression or function with regard to x only, no y's. So what is f of xy that makes this work? You can set them equal to each other if you want and check it out. It's kind of cleaner if you don't, I think. Here we've got the term x squared y. We've got the term x squared y. Right, here we've got the 1/2 y squared, and here we've got the p of y. So the p of y can be equal to this, and then the q of x is 0. Right, we don't need it there to get an actual function that fits both of these descriptions. The actual function that fits both descriptions is x squared y plus 1/2 y squared. So that is the potential function for this vector field. Right, the gradient of f is equal to that. 2x y, x squared plus y. Okay, so this line integral, so we don't even need r at all. We don't even need r. So by the fundamental theorem of calculus, where's that curve? Let's get a copy of that curve. The vector line integral over this curve C is just equal to that antiderivative x squared y plus 1/2 y squared from the beginning endpoint to the endpoint, the beginning point to the end point. So this is equal to 3 negative 1, so that's minus 9 plus 1/2 minus, then it's 0, 2, 0 plus 2. Right, so I have minus 7, or no, minus 11 plus 1/2, so that's 22, so it's minus 21 halves. Okay? Very simple. Just the fundamental theorem of calculus all over again. Right, let's review that example real quick. Okay, we want to calculate this line integral where c is any continuous curve from the beginning to the end point, the beginning 0, 2 to the end 3, negative 1. Since we're not specifying c, it must be that c doesn't actually matter. What actually matters is just the beginning and the end. And we're going to calculate it twice. The first calculation is going to be with the fundamental theorem of calculus. So let's double check that this vector field is conservative. Okay, it's got to be, because, you know, I mean, I didn't tell you what c is, so it must be that c doesn't matter. But let's double check. So p is the 2xy, q is the x squared plus y. So the derivative of p with respect to y is 2x, derivative of q with respect to x is 2x. So they're equal, so it is conservative. So p, which is supposed to be the derivative of f, the potential function f with respect to x, is 2xy. Q, which is the partial derivative of f with respect to y, is x squared plus y. Now you do the antiderivative with respect to x squared y plus an arbitrary constant. For partial derivatives, an arbitrary constant is a function of y. Antiderivative with respect to x squared y plus 1/2 y squared plus an arbitrary constant. Here the arbitrary constant for partial derivatives with respect to y is just a function of x. So now you need fxy that fits both of these descriptions. Fits both of those descriptions. Well, both have the term x squared plus y. Here's a p of y, here's a 1/2 y squared, so just let p of y be the 1/2 y squared, and then there's nothing left, so the q of x can be 0. And that has to work. There can't be a way for that not to work when it's conservative. If the vector field is not conservative, then there won't be any way to make this process work. So fxy equal to x squared y plus 1/2 y squared is a potential function, and the gradient vector field is this, as you can see just by taking partial derivatives. So by the fundamental theorem of calculus, this line integral over c for this gradient vector field is f of xy from end minus beginning, minus 21 over 2. So let's do the calculation again. And let's let c, we're actually going to use c this time, be the following. So we have one of the points 0, 2, and 3, 1. So I'm just going to take the line segment 3, negative 1. The line segment from here to here. And how do you parameterize that? Well, the vector between these 2 points is 3, 3. So we have x equal to the beginning endpoint, 0 plus 3t. Y equal to the beginning endpoint, 2 plus 3t. 0 less than or equal to t, less than or equal to 1. So I got r of t is equal to 3t, 2 plus 3t, 0 less than or equal to t, less than or equal to 1. So that's a standard parameterization of that line segment between these 2 endpoints. So now, just by the definition of what the line integral is, I've got pages. So now calculating the line integral strictly by definition, we get the following. Right, that the line integral over c, right, of f dot dr is equal to the integral from, well, this one is 0 to 1, well, we'll say a to b. Integral from a to b, f of r of t. So, well, what is that function? Let's write it down. Where's it? 2xy x squared plus y. 2xy x squared plus y dot dr. So that's equal to the integral from a to b, so that's f right there. F of r of t dot r prime of t dt. So it's integral from 0 to 1. Right, what's f of r? Right, well, r, right, so f is equal to this. 2xy x squared plus y. R is equal to 3t, 2 plus 3t. Oh, I'm sorry, it's minus 3. I thought something was wrong. 3 minus 3 minus 3t minus 3t. No problem. 3t minus 3t. So f of r of t is equal to, so x is 3t, 2 minus 3t. So I have 6t, 2 minus 3t, comma, x squared, 9t squared, plus 2 minus 3t. Right? X is equal to this, and y is equal to that. So you just substitute those expressions for t into the function f. So this is 6t times 2 minus 3t, comma 9t squared minus 3t plus 2 dot r prime. Well, r prime, right, is just going to be equal to 3 minus 3, which is the slope vector for that line, dt. Right, so this is equal to the integral from 0 to 1, 18t times 2 minus 3t minus 3 times 9t squared minus 3t plus 2 dt. Integral from 0 to 1. Alright, so I have minus 18 times 3, 18 times 3, 30, 54, minus 54t squared, minus 27t squared, so that's minus 81 t squared, right? Minus 81t squared, and now I've got 36t minus 9t. 36 minus 9 is 27 plus, minus 6 dt. Okay, so what do we get? Minus 81 over 3 t to the third plus 27 over 2 t squared minus 6t from 0 to 1. So 81 over 3 as 27 plus 27 halves minus 6. So positive 27 halves, no, minus 27 halves minus 12 halves, so that's minus 11, minus 27 minus 12, minus 39 halves. Minus 36 plus, plus 36 plus 9. Plus 36 plus 9 is 45. Right, that is plus 36t plus 9t, so that's plus 45t, so that's 45 over 2, 45 over 2. So what's that? Minus 50. So let's calculate that. Minus 54 plus 45 minus 12 over 2. So that's minus 66 plus 45, 21. All right, same answer as before, as it should be. Minus 21 halves. So the fundamental theorem of calculus for line integrals, as you notice, is stated just as, it has its own statement, but, some interesting consequences for the fundamental theorem. If curves C1 and C2 have continuous curves, continuous with the same endpoints, then the integral over C1 of gradient f dot dr is equal to the integral over C2 gradient f dot dr. Doesn't matter what the curve actually is, right? So we use just a line segment in the last example. You know, if this is C1, is any weird curve, well, you might as well just take the straight line or some other curve that might be useful for you. That's C2. So that's something that's a little more interesting than the ordinary fundamental theorem of calculus. With the ordinary fundamental theorem of calculus, I mean the integral from A to B, well, the path from A to B is always just the same. It's just that straight line segment. You know, except maybe if you go backward and then forward, or, you know, I mean, there's no real variation possible. But here, there's lots of variation possible between 2 points. I mean, you have infinitely many paths between them. So that's the first one. The other one that's interesting is if C is a continuous closed curve, then, now closed curve means it begins and ends at the same point. So C begins and ends at the same point. Then the integral of gradient f dot dr, well, it's equal to f at the end minus f at the beginning. But the beginning is equal to the end, so it's just 0. Right? So over any closed curve on a conservative vector field, the line integral is 0. Pretty cool. So just one bit of warning before we finish this section. So remember, however, if PQ is not conservative, then the fundamental theorem doesn't apply. Not that there isn't other things you can do, which we'll cover in the next section on Green's theorem, but like for example here, right, there was that real simple vector field we have been talking about, that whirlpool vector field, you know, over the last couple sections. Here, P with respect to y, and so P is equal to minus y, and the partial derivative is minus 1 with respect to y. Q is equal to x, and the partial derivative of q with respect to x is 1, right? So it's not conservative. So you can't find a potential function. There's nothing that would work for a potential function, and so the fundamental theorem of fundamental theorem of calculus for line integrals won't apply. Okay, but in the next section we're going to talk about a theorem that does help in those instances called Green's theorem. But you know, that's the end of the lecture, and we'll have plenty of examples to do in class.